Hello everyone, my name is Jingyi and I'm here to present work done in collaboration with Joel Brandt, Radomír Mech, Maneesh Agrawala, and Jennifer Jacobs on supporting visual artists in programming through direct inspection and program execution. Programming is a powerful tool for visual artists. They can define abstractions to repeat and transform data or incorporate data that would otherwise be tedious or impossible to do by hand. Programming is also notable for its ability to support artistic exploration. The exploratory properties of code are evident in this quote by Colette Bangert describing her and her husband's early work in the 1970s using algorithms and a plotter to create abstract drawings. That it is possible to use mathematical formalism and pure geometry while attempting a humanistic exploration, to us, is one of the primary advantages of the use of the computer as a drawing medium. As suggested by the previous quote, traditional visual artists also depend on exploration. However, they do so in very different ways than programmers. Manual visual artists primarily explore through visual sketching. Often, their ideas emerge through reacting to this exploration, reacting through their eye, to their hand, to their pen, to the page, a tightly coupled iteration loop with manual tools. In contrast, while the medium of programming offers new opportunities for exploration, existing programming tools can conflict or hinder exploratory workflows from manual art. Conventional software development traditionally involves more linear structures and working towards a predefined goal. Existing programming tools, despite being geared towards artists, reflect the conventions of software development workflows and their features and interfaces. Iteration is slower as artists have to compile code and fix syntax errors, and they need to know which lines of code control which aspects of their artwork. Furthermore, programming is symbolic. Programming environments reflect the structure by requiring artists to edit abstract descriptions of artifacts rather than the artifact itself. While editing symbolic code can be a powerful form of expression for experienced programmers, it can pose challenges for artists who are first learning how to program. Like many other new programmers, artists learn from examples. So here on the screen, we see a common workflow, which is browsing some example artworks, choosing one that they like, and starting by modifying the skeleton code provided. Since art is a field centered on originality, it's important for visual artists to extend these examples to create original work. However, artists need to understand algorithms before they can make unique works. This is something highlighted by Marius Watts, who criticizes the lack of complex modifications in a lot of generative art, such as an over-reliance on Voronoi diagrams, some examples which you can see on the left. Going back to the workflow, since most creative coding tools don't offer support in understanding the algorithms behind the example code, artists are often left tweaking input parameters, which results in a narrow space of artifact changes. And sometimes they're left wondering why a change they made is presenting them with a blank canvas entirely. So to investigate these differences in workflow and manipulation, we conducted a formative study. We were curious about the differences of how visual artists versus people with backgrounds in software development approached understanding programs that created visual art. So we asked 2 artists without programming experience and 2 computer science grad students to use an early version of our system, which I'll explain in more detail shortly, and reason about a brush that produced a spiral as they drew. We saw that the computer scientists read data values from a table, trying to do mental math to understand the geometric transformations being applied. In contrast, we saw the artists make many strokes with a spiral brush, responding to and reasoning about how the artwork changed with their manual inputs. And recognizing the power of symbolic programming for artists and the challenges they, accustomed to visual and direct interactions, face in understanding these symbolic programs, we hypothesize one way to make this easier is by providing explicit links and visualizations of program parameters and state with the in-progress artwork. As such, we built program inspection and control tools on top of the creative coding system Dynamic Brushes. For a quick background, Dynamic Brushes is a system that allows artists to make custom brushes on a desktop programming interface and then use these brushes to create visual art on the iPad drawing interface. The core of the Dynamic Brushes programming model is in creating brushes. Brushes are just mappings of input data, like a synthetic square wave or the stylus position, to brush properties such as Y-scale or rotation. And as artists draw with their stylus, they can observe the outputs of their brush program on the iPad. Demystified Dynamic Brushes, or DDB, extends the Dynamic Brushes programming and drawing environments with linked visualizations and interactions to examine program parameters and state. For example, numeric readouts on the code here are linked to visualizations and labels on top of the artwork here. While I won't touch on every new feature in this talk, I want to focus on the ones that best enable artists to explore code while engaging in the process of drawing and make explicit connections between the artwork and the code. First, DDB has visual inspectors that lie on top of artwork that show otherwise invisible parameters. Second, DDB's direct selection feature lets artists touch their artwork to jump their program state to when that point was drawn. And third, DDB lets artists loop past inputs to the system, which lets them control program execution at a pace aligned to their drawing to immediately observe the effects of their brush changes. So we hypothesize that the design of these features will help visual artists better understand and author programs. But before we get into the details of DDB, I wanted to briefly touch on some related systems. First, there has been a variety of domain-specific creative coding systems aimed at artists, whether they're textual, like processing or open frameworks, or node-based, like Grasshopper or Max. These symbolic languages are extremely expressive and powerful, but they pose barriers in understanding code. While built-in debugging tools exist, these tools are modeled after those commonplace in other software engineering systems, such as numerical readouts or line-by-line execution tracing, without special consideration for the visual art domain. Research has also developed linked environments, like Sketch and Sketch, which aims to combine direct manipulation and programming in creating SVG images. Our goal is different. We want to create visualizations and interactions that allow artists to understand parts of their program, align with their existing workflows. HCI research has also investigated how to best support program comprehension for software engineering. For example, asking questions about code outputs, proactively visualizing runtime states while the user programs, and linking HTML and JavaScript to help users filter the relevant lines of code of front-end elements. We take inspiration from these features from general software debugging tools in developing DDB. From our formative studies and motivations, we developed a set of design goals for DDB. First, since programming allows for arbitrary mappings of input to program state to output, we want to visualize all three of them together to help artists understand their relationships. Second, we saw artists trying to understand code by drawing, an action that aligns with the principle of epistemic action. Thus, we want artists to be able to manually manipulate their artwork to reason about their programs. Third, to leverage artists' familiarity with working concretely, we also want to provide concrete representations of program behavior. And finally, as artists work quickly, iteratively, and reactively, we want to let them edit code, observe the results, and return to manual drawing in rapid succession. To illustrate these design principles, I'm now going to present the system with a walkthrough scenario. We'll follow the artist Jo as she modifies an example brush, using DDB's features along the way. So it's common for both artists and programmers learning a new system to start with examples. So Jo starts by loading an example brush program. Experimenting with it, she notices that it is a mirror brush. Jo first wants to understand what is causing that mirror behavior. First, she uses the visual inspectors. These help by displaying normally invisible data like stylus input paths or brush properties to help artists reason about the programs. Furthermore, because numerical labels appear next to the artwork itself, artists don't have to interrupt their drawing process and context switch into reading a table of values, in contrast to debugging methods in existing creative coding systems. So Jo toggles on the visual inspectors that appear on top of her artwork, which allows her to access information about her program values as she draws. The mirror brush here is defined by two strokes, two separate brush behaviors, brush A and brush B. Jo takes a look at the brush icon for the right side behavior, which shows geometric properties like scale, rotation, and the brush origin. She can touch the other stroke to see the properties of the other brush program. She notices that the x-axis scale is flipped on the brush icon, so she touches it, which also highlights it in the table of numeric readouts in the code. Jo notices that this divergence in values is what causes her output to mirror. Now that Jo sees a visualization of why her brush mirrors, she wants to make changes, so she uses looping. DDB's looping is designed to let artists focus on exploring and quickly changing values while they're engaged in drawing. With looping, they get immediate feedback about their brush changes while holding the stylus input constant. So Jo toggles on loop mode here at the bottom and starts experimenting with different mappings in the programming interface, which are these overlays with the black backgrounds. So here she's changing the output of the left-hand side of the brush, and she's just dragging in some different values to explore what they look like, and she stops exploring when she maps a square wave to the scale Y property, as this produces an interesting result that she wants to keep. For a more fine-grained understanding of what's happening to the square wave, Jo turns to stepping. Stepping, like looping and direct selection, is another way to control program state and visualize incremental changes to artwork. But like traditional software debugging tools, stepping requires a slower and more methodological inspection of program parameters. So back in the programming interface, Jo turns on step mode at the top, and now she wants to step through lines of code. So she uses the arrow keys to step through the program state and parameter mappings, which are being highlighted, and her drawing incrementally updates alongside her steps. Jo takes a look at the visualization of the square wave in the top corner. She notices that when its value is 1, the output, indicated by the purple dot, matches the brush position, indicated by the red dot. But when the value of the square wave is 0, the scale y-axis disappears and the output jumps back to the brush origin. So through observing these visualizations, Jo now understands the relationship between the square wave input, the intermediate brush position, and the output. Now, having made a geometric change, Jo wants to make a color change. So back in the program, she hovers over lightness and hue to see the range of accepted parameters, changes lightness to 1, and then drags in a sine wave for hue. These values result in a rainbow stroke. So Jo particularly likes the shade of blue that she sees, so she touches it with her finger to jump her program state to when that blue stroke was drawn. So she uses the direct selection feature, which allows artists to expose which numerical parameters correspond with which aspects of their drawing they're interested in. They can recover and reason about program state through directly interacting with the artwork, as opposed to working from code, like in existing systems. Jo now reads the upper left corner, and she sees that the blue hue corresponds to a sine value of 0.66. With this numerical knowledge, Jo returns to looping, writing an expression that constrains the hue range to blue. She repeats these edits to the right-hand side brush behavior, and now Jo has successfully made her own modifications to the mirror brush. Developing a system that links symbolic programming with a drawing environment provided us an opportunity to observe how artists moved between and relied on inspection and debugging tools. In particular, those like stepping that mirrored ones in conventional software toolkits versus those specifically designed to be in the drawing environment. So now I'd like to transition into what we learned when we observed visual artists using DDB and what that implies for the future programming support tools for visual artists. First, we conducted an observational study with 5 artists with no programming experience. We asked them to modify 3 starter brushes on the left into target brushes on the right, followed by an open-ended brush creation time. Our goals in the study were to observe what inspection features participants did or did not use, and how and when they transitioned between the programming and drawing environments. Artists in the study practiced a range of approaches, which can be found in the paper, but for the sake of time, we'll focus on the main takeaway. Participants predominantly use the visual inspection and looping features. This matches with our motivation that artists work by exploring and reacting to their artwork, as these features are in line with their current practices. We hypothesized they did not rely as much on numerical inspection or stepping, 2 methods of program comprehension common in normal software engineering, due to these features requiring their attention be taken away from the drawing. So based on our observations, we now present a few design suggestions for future work into programming comprehension tools for artists. The first is to display numeric information in relationship to the artwork. Although the numerical inspectors in the programming interface and the labels next to the artwork contained the same information, artists said that they were overwhelmed by the table of numbers, but often referenced and used the information when it was just present next to their art. In comparison to traditional software debugging tools which provide numeric information relative to the code, programming environments for visual artists should display this in the execution environment in relationship to the in-progress artwork. Second, one common reasoning mistake we saw was participants choosing the wrong kinds of input data if they could not perceive any major visual changes in the drawing, even if the data numerically changed. For example, in the spiral task, some participants struggled because they didn't multiply their chosen generator, which has a range from 0 to 1, by 360 for a perceivable rotation, so basically they were just rotating between 0 and 1 degrees. So, to guarantee perceivable outcomes, future tools could allow artists to manually manipulate artwork, program state, and input data to understand code. For instance, on the brush inspector, they could stretch the axis to change the scale parameters. Finally, while traditional software engineering debuggers assume that input should be held constant within the system, we saw one artist manually redrawing inputs as they wanted to experiment with controlling different gestures, such as stroke speed and weight. Instead of perfectly playing back input data, future tools should support examining programming performance across a variety of different manual inputs. These design principles share a common theme, which is that while symbolic programming is a powerful tool for art, assumptions from traditional software debugging tools do not hold for artists. So instead, let's make program comprehension tools support workflows that are exploratory, concrete, and manual. Thank you for your time, and one last thing, This work was done in collaboration with Jennifer Jacobs and the EXPRESSIVE Computation Lab at the University of California, Santa Barbara, and ECL is currently seeking PhD students, visiting students, and postdocs, so if you're interested in this work, please reach out to her. She is a great collaborator. Thank you.